Hello, this is the second video of this week 5 and we're going to be focusing on artificial neural networks in this video. We start with the core component of the neural network, which is the neuron, each of the nodes of your network. The general structure design of these algorithms is trying to mimic what happens in a human brain. So we have nodes, each neuron, and then there's connections with the other neurons. And we need to calculate mathematically what input values and what previous learning triggers a connection between a neuron and the neuron beside it. So an artificial neural network will have a set of input values that are entered into it, then a set of weights that connect, that give a weighting to each of the connections between this neuron and the other neurons around it. The activation values, which are the output that you get when you use your activation function, combining your input values with the weights. And remember, the weights will be adjusted at the training time. The network topology telling you these neurons connections. So from this neuron, where can you trigger an output? Where does it go? What other neuron is connected to it? And the learning algorithm, or in other words, how are we going to make these weights adapt to and learn the particular problem that we're interested in. So if we look in detail at those components, your input values, they come from your external environment, your particular problem, your features, or they could, if you have several layers, they could come from the activation of other neurons. And sometimes they need to be discrete values, 0, 1, or from -1 to 1, so they've been standardized to be within that range, or sometimes they can take any value. We have our set of real valued weights, and they are usually initialized to some random values, and during the training phase they change to actually model the actual problem that we're looking at. Your activation values are the outputs from each of the connections, or each of the neurons into each of the connections, and they could become the input to another neuron, or it might just be a value towards the output of the system. Then we have the activation function that uses the input data and the function, and the weights, goes through the activation function, whatever mathematical function is, and we'll see several of them in the next slide, and gives you the activation value. So it gives you the output, takes the inputs with the weights, does some maths between those values, and gives you the output. So the behavior of the neuron can be considered as a mathematical function that combines your weights with your inputs and gives you the output. Now we have the slide with the different activation functions. These are some of the basic ones, the most common ones. So you can have them unipolar or bipolar, we'll see it in the graph in a second, and hard limiting, linear, saturated linear, log sigmoidal, tangent module. The basic difference, if we have them unipolar or bipolar, bipolar meaning you have two values here, -1 to 1, unipolar either nothing, 0, or 1. Then we have our hard limiting, is literally either this value, nothing in between, or that value. When you have a sigmoidal, you get a curve, so you can have values in between. It's not literally goes from 0 to 1 straight away, so you could have 0.9, 0.2, and so on. We have here different types of sigmoidal functions. We just need to know the main characteristic is if it's unipolar or bipolar, but we're not going to be playing too much with these functions. We just need to know they exist and that we can get different results using different functions. Now we're going to look into a particular problem, the AND and OR problems, and using perceptron, which is, we're going to be using a single layer perceptron, which is one of the most basic neural networks and one of the first ones to be implemented. We can calculate, as I was saying, the AND and OR functions from our logic, if you remember from second year. Now we will also see that we cannot represent the exclusive OR. Remember, it's the OR function that will only be one in the output when both inputs are different. When we looked at the normal OR function, the traditional OR function, we had a 1 in the output whenever one of the two inputs was a 1. And we will see that to implement AND and OR functions, we can use a single layer perceptron, but to implement an XOR problem, we will need a hidden layer. And this is an important concept because we will see how more complex problems can be solved using neural networks if you add extra nodes, extra neurons, and extra layers in between the input and the output layer. So we'll use this example, this XOR, as our example to see why this is happening. Okay, let's have a look at the OR. First of all, we're going to look down here at our truth table. Let's see if we all remember. So if we have 0, 0, we get 0. 0, 1, as long as one of the two inputs is a 1, we get a 1. 1, 0, we get a 1, and 1, 1, we get a 1. Okay, so now we look at our perceptron neural network. We have our two inputs. They go into our first layer with our neurons, and there's no threshold here, so we just get our value. So let's say we look at the first row, 0, 0. So this is a 0. We have a multiplied by 1 here, and the other 0 goes in and it gets multiplied by 1. 0 plus 0 is 0, and we have here our activation unit in the output layer is telling us that we need a threshold of 0.5 to get a 1 in the output, because we're getting 0 and 0, nothing comes out, we get a 0 in the output. Now we move to the second row, 0 and 1. 0 goes through here, multiplied by 1 is 0. Then we have a 1 coming through here, multiplied by 1 is 1. 0 plus 1 is 1. The threshold is 0.5. 1 is greater than 0.5, therefore we get a 1 in the output as it's happening here. Same thing is going to happen with the 1 and 0. 1 multiplied by 1 is 1. 0 gives us 0. 1 plus 0 is 1. And the threshold is 0.5. It's greater, our value is greater than 0.5, therefore we get a 1 in the output. And then for 1, 1, same idea, we get 2 when we multiply them by the weights, and 2 is greater than 0.5, so we get a 1. Now if we want to implement an AND function, first of all we do the same, we look at the truth table. Remember, an AND function was a function, that a logic function that will give us 1 only when both values are 1. It's like a multiplication. So in this case we still have no threshold for our input layer, nothing stopping here, our inputs, they get multiplied by 1. Now we have a threshold of 1.5. What's going to happen is 0 and 0 will give us zeros, and we get a 0 on the other side. 0 and 1, or 1 and 0, will give us a 1 here, which is below the threshold, therefore 0 on the output. And only in the case where we have 1 and 1, we'll get a 1 on the output. 1 multiplied by 1 is 1. 1 multiplied by 1 is 1. 1 plus 1 is 2, and that is greater than 1.5, and therefore we will get a 1. Now we can use just an input layer and an output layer and get an OR or an AND logic function working after we have adjusted the weights and the threshold to the correct value. Now these two functions are what are called linearly separable. So if we were to plot the points in a XY two-dimensional space or in more dimensions, you would see that you can have a line that will separate all the points. Now when we look at the XOR problem, you would see that there will be no line. You cannot find a line, we'll see it in the graph here. Okay, so for the AND and OR, you would get something like this, where all the values that should be 0 are in one corner, all the values that should be 1 are in another corner, and you can put a line in between that separates both. That is called linearly separable. Now when we look at the x-score in a minute, we will see that our values are not linearly separable. They are mixed in a way in our 2 dimensions, in this case, where there is no line that we can put through the data that will split it into the ones that should give you 1 and the ones that should give you 0. Let's have a look at the XOR. So remember, XOR is exclusive OR, so 0, 0 is 0, the same as the normal OR, but 1, 1 is also 0. You're only going to get a 1 in the output when you have one is positive, one is negative, one is 0 and the other one is 1, or 1 and 0 here. If we put those in an XY axis, we'll have 0, 0, 1, 0, 1, 1, 0, 1. There is no line. If I put a line vertically here, I have a true false on the left, a false true on the right. If I put a line horizontally, if I put a line some kind of diagonal, I still have these other truths here. So there's no line that will subdivide a plane in a way that all the truths are on one side and all the false are in another side. And this is called linearly inseparable. So what do we do to solve a classification problem where we have a linearly inseparable task? Well, what we need to do is add this hidden layer. There's an extra layer that is adding a value and extra weights, and then the final threshold is not going to be just made up of the input multiplied by the single weight. Okay, so let's have a look at this truth table. We have 0, 0 should give us 0. We have 0 here, 0 here. We have our hidden layer with a threshold of 1.5 on the neuron. The weights are 1 and 1 here, 1 and 1 going from the input layer towards the output directly. But we have a -2 connecting the hidden layer to the output layer. So we have 0 here, multiplied by anything is 0, multiplied by anything is 0, 0, 0, everything is 0. That's below the threshold, so that gives us 0. That's clear. If we have 0 and 1, this one is 0, going in, 1 goes multiplied by 1 is 1, but we have 0 going here. Sorry, this one was 0, multiplied by 1 is 0, 0 multiplied by 1 is 0. We have a 1 coming through here, so we have a 1 and a 1 up here. This one plus the 0 coming from this one does not activate, we get a 0, so that goes in, 0. So we have 0, 0 and 1. Okay, you might want to do this on paper to follow the steps, and 1 is greater than 0.5, so we get a 1 in the output. Same thing is going to happen with 1 and 0. The 1 will come through here and goes in here, doesn't activate this one. The 0 goes in and we get a 1, and that gives us a 1 on the output. Now if we look at the last case where we have 1, 1 on the input, we have a 1 going through here, another 1 going through this one here. So at the moment we have 2 up here that is greater than 0.5, but then the hidden layer is going to give us 1 and 1 is 2, which is greater than 1.5, and that gives a -2. So we had 1 plus 1 is 2, minus 2 is 0, which is below 0.5, below the threshold, and we get a 0 in the output. Okay, so as I said, I would recommend taking paper and pen and following each of the inputs, do a diagram for each of the 4 different cases. So you can see how by adding this extra hidden layer, we can represent a problem that is a lot more complex than what we had done before with just an input layer and an output layer. So the general process of training the neural network follows the following steps. Initially, you get your weights initialized as random values, and then your training set contains a number of inputs with the known correct output. When you enter your input, it goes through all your weights, then it gives you an output. You know what the target value of the output should be, you compare it, and the algorithm will readjust the weights to make sure next time something similar to what you just saw comes in, you get something similar to what you know should be the value, the target value. So you use the error, the difference between the given output and the truth output to calculate that adjustment of the weights. One typical adjustment algorithm is the backpropagation algorithm, but there's many others. Now we're going to have a look at a kind of more complex problem and how, without getting into details, just that use of this hidden layer. So if we're looking at face recognition, your input layer are going to be different pixels from the image, and then at the end your output is this a face? Is there a face in this particular part of your image? And the answer will be yes or no. So what the hidden layer in the middle is going to do is split the task, which is a very complex task, into different tasks or subtasks. So is there an eye in the top left? Is there an eye in the top right? Is there a nose in the middle? Is there a mouth in the bottom? Is there hair? And after each of these smaller tasks have an output, yes or no, the combination of all those will give you the final answer. So the final, if it is a face, you will have most of these being activated, but maybe not all of them. Now if you look inside each of those layers, inside the hidden layer, is there an eye on the top, in the top left, as we saw in one of the sub problems? That can be split again into, is there an eyebrow, is there eyelashes, is there an iris, and so on. So this gives you an idea of why the concept of deep learning and deep neural networks, where you have extra hidden layers, is very powerful, because you can split the problem into several subtasks and go deep into the problem, and at the end each of the smaller problems is made out of certain characteristics that need to be fulfilled, and or a majority of this group of characteristics need to be fulfilled to give you a partial answer, and then the addition of all those partial answers with all their weights and activation functions and so on can solve a very complex problem that otherwise we wouldn't be, with just one input layer and one output layer, we would not be able to solve. And we have a summary of deep neural networks on this slide. Okay, now I'm gonna finish this video, and I will give you another video where I'm gonna show you an example of using neural networks using MATLAB.